Hey everyone, and welcome to The Explainer. Today, we're diving into something absolutely game-changing. We're looking at how you can locally fine-tune large language models right on your own consumer hardware. If you've been wanting to get into local LLM fine-tuning as a hobby, you're in exactly the right place. We're going to walk through a really fun, multidisciplinary curriculum of pedagogic projects, specifically designed to help you learn the ropes. We've got incredibly diverse, easy-to-work-on scenarios to build your skills today, from low-resource linguistics like polylanguage and Tipitaka study, to headless, dark factory vibe coding with Haskell, and even applied real-world domains like pet care, taxes, and Medicare. Here's how we're going to break it all down today. First, the local AI revolution. Second, tools for the hobbyist. Then we'll hit our specific paths. Track 1 is ancient languages. Track 2 is vibe coding. Track 3 is applied domains. And finally, your fine-tuning curriculum.
All right, let's kick things off with Section 1, the local AI revolution.
Okay, let's dive right into this. You see, the big takeaway in this revolution is that fine-tuning is no longer a luxury reserved for those massive enterprise multi-GPU clusters. It's a reality for your workstation hardware right at home. But to understand why this matters, we have to look at the difference between fine-tuning and context engineering, or, prompt engineering. Context engineering shapes prompts for general models, and hey, that can take you pretty far, but it has its limits. If a base model doesn't understand the nuance of your specific domain, like strict precision, specific reasoning styles, or really specialized jargon, no amount of prompt shaping is going to consistently close that gap. Fine-tuning, on the other hand, that's the process of actually modifying a pre-trained LLM's internal weights. You're directly baking that specialized domain knowledge right into the model's brain.
So you might be wondering, how do we actually pull this off on a home setup? Well, this is where parameter-efficient fine-tuning, or PEFT, and specifically a technique called LoRA, low-rank adaptation, come in. Full fine-tuning updates all the parameters, which is frankly hugely expensive. But LoRA, it updates only a very small subset of weights while freezing the rest of the pre-trained parameters. This drastically reduces the compute costs and the VRAM you need. It literally democratizes AI by allowing massive models like Llama 3.1 to be fine-tuned on standard consumer-grade hardware.
Moving right along to Section 2, tools for the hobbyist.
Let's look at the actual software stack that makes this whole local development ecosystem a reality. Depending on your setup, there's a fantastic variety of tools out there. If you're bootstrapping or maybe just starting out on a mid-tier GPU, Unsloth Studio is incredible. It provides a no-code interface and can actually slash your VRAM usage by 70%. It's perfect for beginners. Now, if you're deep in the Apple ecosystem, MLXtune is specifically optimized for Apple Silicon, which lets you fine-tune adaptively right on a 24GB Mac. And for those of you scaling up to mid-size or more advanced research setups, frameworks like Axolotl and TorchTune provide those robust, multi-GPU production environments you'd be looking for.
And the modern advancements in local optimization, they are just incredible right now. We're seeing methods like L4Q push performance right into that top right quadrant of efficiency. It gives us the absolute best of both worlds, high accuracy and common sense question answering, coupled with incredibly fast inference speeds. This is exactly what empowers local developers like us to build highly capable, responsive models without needing a literal supercomputer in the basement.
All right, let's jump into Section 3. This is Track 1, Ancient Languages.
Let's start our curriculum by looking at low-resource computational linguistics using the ancient Pali language and the Tipitaka. We're starting with a really interesting data sourcing challenge. So Sutta Central hosts these incredible segment-by-segment bilingual alignments of the Pali Tipitaka. However, they explicitly and very politely request that their canonical Theravada Buddhist texts not be scraped or used in any way to create datasets for generative AI. So as developers learning to fine-tune, we must impartially respect this request while still figuring out a way to train our language models.
So what's the clever workaround here? How do we respect that boundary?
Well, we synthesize parallel sentences using the rule-based Digital Pali Dictionary, or the DPD. By parsing the DPD database, developers can programmatically generate synthetic, grammatically diverse sentences. This actually teaches the model the root morphology and complex Sandhi structures of the language, completely from scratch, all without scraping or using Sutta Central's direct scriptural records. It's just a brilliant pedagogic exercise in natural language processing.
But wait. You can actually take this a step further into multimodal AI, which is objectively fascinating.
You can fine-tune Polygamma, which is a 3 billion parameter vision language model. By training it on custom image text pairs, the model actually learns to map visual patches of historical palm leaf manuscripts directly to Romanized Pali. It decodes the physical document artifacts and regional scripts. So you're basically turning your computer into a powerful local tool for actual historical preservation.
Let's shift gears now. Section 4, Track 2, Vibe Coding. Moving into mathematical reasoning and code generation, let's see how this builds into an autonomous system. If you've wanted to learn the Haskell programming language, this is an incredible pedagogic project to tackle LLM hallucinations. You set up an autonomous Haskell coding loop, essentially a dark factory for vibe coding. The fine-tuning pipeline streams source files, the agent generates Haskell code, and then it's checked against the strict GHC compiler. If there are compile time errors, like a type mismatch, that output is fed directly back to the LLM. This headless, automated feedback loop literally forces the model to self-correct and learn to write perfectly verifiable functional programming code without any human intervention.
Building on that need for strict correctness, we can also fine-tune models to write Prolog or Datalog. These logic programming languages model real-world domains through explicit relational facts. By using tools like Logica to compile these logical structures into executable queries, we guarantee the reasoning is verifiable. This stops the model from conversationally hallucinating answers and instead grounds the AI in explicit facts.
Which brings us to Section 5, Track 3, Applied Domains.
Let's look at fine-tuning for highly regulated real-world areas like taxes, legal compliance, Medicare, and veterinary medicine. When you compare these tasks, veterinary health offers a fantastic starting point for beginners, specifically patient de-identification using the SAVSNet and PEVAL datasets. Now, if you want something a bit more intermediate, you can tackle legal and Medicare compliance using datasets like Legal QAV1 or Insta150KV2. In those legal domains, the model has to learn to extract explicit arguments and map complex administrative decisions directly to statutory law without losing any contextual fidelity.
Let's zoom in on that beginner veterinary task for a second. 17,600. That's how many professionally annotated veterinary electronic health records are in the PetEval dataset. If you have any interest in dog care or general pet health, this is a perfect project that is super easy to work on and learn from. You use this free text clinical data to teach the model named entity recognition. The model learns to strip out personally identifiable information, replacing real animal and owner names with HIPAA-compliant pseudonyms, all while keeping the underlying medical facts totally intact.
All right, time to wrap it all up. Section 6, your fine-tuning curriculum.
Let's bring all these distinct pieces together into one unified strategy so you can actually start building. Here's your learning path. You can start as a beginner with pet-patient de-identification, learning basic sequence labeling, and named entity recognition. From there, you graduate to intermediate tasks like rule-based polytranslation or building a headless vibe coding agent to really learn about those compiler feedback loops. And finally, you can push into advanced territory with multimodal vision tasks like poly manuscript OCR or setting up verifiable logical reasoning systems using Prolog proving.
It's amazing, isn't it? We've seen how local fine-tuning has evolved from just basic text completion to designing active autonomous systems right on your home computer. Whether you want to master logic programming, preserve historical texts, or build healthcare and compliance assistance, the tools are literally in your hands. So balancing your available hardware with your personal curiosity, which domain are you going to fine-tune first?